Okay, we should be recording. We're going to be continuing on from where we left off last time. And one of the things that I had hoped to do was to add some annotation to the code, and I do plan to do that, but my catch-up time is presumably this weekend to do it. In other words, I'd like to give you first the some comments concerning the R code. This is from my last class, so I want to get rid of it and go into 523. And so I want to start. I have updated the schedule to contain, I think there are a few slots. I updated the schedule with the lecture, and I don't think I changed the notes that are also up there. They should be the same as what I have here, hopefully. So these are the data structures that I was talking about last time, and I want to continue. But before I do that, I had mentioned to you, I think, that we can define the binomial distribution recursively. That's actually true, but I actually meant for the simpler case of the Poisson distribution. And so I wanted to show you, this is a Poisson distribution of the parameter lambda. And the Poisson is very common, in many applications, in many natural applications. You're talking about, if a binomial experiment, you're talking about binomial or Bernoulli trials, where you have n trials, and you get a success or failure, and you're counting the number of successes, so you could get 0, 1, 2, 3, up to n. On a Poisson, you're talking about maybe the number of flaws in a square yard of cloth. And so you could have 0, 1, 2, and technically there's no other limit. So I don't want to spend a lot of time talking about the Poisson distribution here, but this is its definition. We can think of lambda as the only parameter, and lambda will be the mean of the Poisson, and the mean, but the Poisson also has the characteristic that the variance is lambda too. And so e to the minus lambda, lambda to the y over y factorial, where y is the value of the random variable. And y can take on values 0, 1, 2, 3, indefinitely. There's no upper limit like there is for the binomial. Although realistically, of course, if you were talking about the number of flaws in a square yard of cloth, there is an upper limit. But it may be quite large. So if I have this distribution, if you look at that definition, I wanted to show you in a sense what I meant by recursive. I meant really recursive in y. So if I compute the probability of p of y, you can show by some fairly simple arithmetic that that's the same as the probability of y minus 1 times lambda over y. So with the binomial, so this is the Poisson, and you can see there's this very simple relation. So the Poisson is defined in terms of itself. And in R, we can recursively program this, and this is actually the recursive code to do that. Recursive Poisson is a function, and it says if y equals 0, return e to the minus lambda. So if y is 0, if you look at the definition, of the Poisson, where is the definition? Somewhere up here. If y is 0, I have e to the minus lambda, lambda to the 0, which is 1, over 0 factorial, which is 1. So it's e to the minus lambda, right? But, and this is useful to know, so So here's my function. It says if y equals 0, return e to the minus lambda, else, so this is what's called an if statement, if else. If this is true, do this, else do something else. And what I do is return the same function, recursive POIS, with argument y minus 1, okay, times lambda over y. So this is what's called a recursive function. In other words, the function recur.poise is a function. The name of the function is recur.pois. It's defined in terms of itself. In other words, the function name is inside the function also. But inside the function, I'm using the argument y minus 1. So then when it calls that one, in turn it will call y minus 2 and y minus 3 and all the way until it gets to 0, and then it returns the value of lambda, and then it works back up, computing all the values of lambda. Recursion is a very powerful way of thinking. Sometimes it may not be the most efficient way of computing things, but nonetheless, it's a very powerful way of thinking about programming. There are a lot of, this is a very common theme among computer scientists, but also among physicists. There's a rather well-known, I think his name is Douglas Hofstadter. I think he was at Indiana University in Indiana. And he's written several popular books on computer science. And one of his books was called I Am a Strange Loop. Anyway, some of these books are quite interesting because they get into very philosophical discussions. And recursion runs throughout his writings. At any rate, so how would you do this with a binomial? Okay, or can you do it? Can you do it, and if so, how do you do it? But the recursion is not, I'm not thinking of recursion in terms of n factorial. Yes, n factorial is part of the definition of binomial, and n factorial can be defined in terms of itself. N factorial is n times n minus 1 factorial, right? So n factorial is a recursive function. Factorial is a recursive function. But I want it recursive in y. Okay, so you can still ponder this. Some of you have written me emails. So let's... So you can, if you want something simpler, you can do the Poisson. Okay, getting back to what we were doing. So I just brought this up, and perhaps just to be a little bit careful, I'm first of all going to get rid of, that was a help file for the histogram. So I'm going to change my screen a little bit, and I'm going, since this is the last class, I'm going to go to the Edit menu and clear the console. And I'm also now going to set the working directory to where I am, which is now in 523/node/chapter2. So I've set the working directory. So for example, if you want to see what's happening, then we can look at the workspace. And so we may want to clear that workspace just to get a clean start. So I've now cleared the workspace. That may get me in trouble, because if I define a y I need that I had previously defined, it's no longer there. So you got to be a little bit careful when you're doing this. So I'm going to leave the workspace there so you can sort of see what's going on. So let me talk a little bit more. I didn't talk I didn't talk very much about machine, sort of the machine characteristics of the machine. But, there's certain machine characteristics, and that depends upon the machine. But, if you try to sort of exceed the limits of what a machine can hold, let's say an integer, then you get an integer overflow. And I talked about that last time. It's just something you can be aware of, that you can get underflows and overflows when you're doing numerical computations. One of the other things you have to realize, and now Aura helps you out on this, is that there's always round-off error. The problem is that round-off error can propagate. And if you have an algorithm that's, say, iterative, and you're actually doing many, many steps, then the round-up error can build up, and pretty soon you may lose a significant amount of accuracy. So the algorithms in R are quite good. And so, for the most part, this doesn't happen in R. Everything is done in double precision, so you have quite a bit of accuracy. And plus, the algorithms underlying, for example, the linear algebra that's used as part of R is a very, very good library. I want to talk about factors again, just a little bit. We talked about it last time, but I did want to mention that, I just want to quickly go through this again, that in this case, I created a factor x, and those are the possible values. But, at this point, I haven't created a factor. So if I say factor of x, it means y is a factor. And now if I print y, you see we have the same a, b, c, d, but now we have levels associated with that. And notice that I no longer have the quotes around it. So you shouldn't think of a factor as just being a special type of vector. I mean, it is a vector in a way, but it has other attributes. And we're really talking about each of the values will be one of the factor levels. So the a, which is a character string, was converted to a, which is a level of a factor. So it's no longer quoted. And if I look at the attributes of a, you notice that there are the levels, and notice that the class is factor. Now, if you actually have data that you've read in, and a lot of times you have a function that reads in, say, what's rectangular type data using a function called data.frame. And if some of the columns have character data, and they automatically coerce into a factor. And if you have numeric values, they automatically get coerced to character. So in other words, if you have some character data in the column of, say, a data frame, everything will be converted to character, and it will be converted to a factor automatically. Now, I went through this example. I don't think I'm going to go. This is where we were actually trying to collapse the levels of a factor. So we had a factor. We had the letters A, B, C, D, E. We had 5. And we were going to take those and group them into 2 groups, Roman number 1, Roman number 2. So this is just a grouping operation to show you how to do that. I don't think I'll go through that again. But I do want to talk about ordered factors just for a second. So if I now take y, and previously I had defined y as a factor, I now use a function ordered, which creates an ordered factor. And now if we look at the class, you see that if I say the class, it gives 2 things. Why? And what does it mean? Well, a class is a structure in which all the objects of that class, of which y is of class factor, and z is of class ordered. But notice it also said that z is also a class factor. So what does that mean? Well, we have what's called multiple inheritance. In other words, z has a, let's go back to y a minute. Y is a factor. Its class is factor. It has the attributes of the class factor. And what are the attributes? Well, the main attribute is it has a set of levels. But when I look at z, which I created from y using the function ordered, it now created an object of class ordered. But class ordered also inherits from any attributes or characteristics of the class factor. So this is called multiple inheritance. In other words, it is of class ordered, but ordered derives from factor. So if you take a class factor, ordered class has the characteristics except that it orders the levels. And so if I print out z, you notice that the levels are now a less than b less than c less than d less than e. There is an order to those levels. Now suppose you don't like the ordering. You have an order, but by default it will either do it in the order in which they arrive, or it will do it alphabetically. But suppose that's not the order you want. Then there's a function called levels, which is actually an attribute, but there's a function called levels which can reassign the order. So ordered factors are important. Why? Suppose you have some disease, and you've categorized a patient according to the severity of disease, sort of low, medium, high. So there are three possible outcomes. So it's a factor with three levels, but they're ordered. And now I want to predict the level. And I may predict it based upon, you may base it on demographic characteristics, or perhaps you could base that on other medical techniques. Perhaps you could even predict it from genomic profiles. So in other words, I want to build a model that predicts the levels. Now the simplest type of model is a binary factor. You have a factor that has two outcomes. Let me put it in the example I was using that Rebecca was working on. I have students, and they get an A, B, C, D, E, A, B, C, D, F, or W. Now let's forget the W right now. Well, okay, let's not forget it initially. So I can make it binary by doing what? The university gets real concerned if our courses have greater than a 30% DFW rate. In fact, I get an email from the associate dean saying, you have these classes that have a DFW rate that's greater than 30%. What are you going to do about it? The only thing I say, well, mathematics is worse. They have a lot more courses that have DFW rates than we do. So, at any rate, but suppose you wanted to predict DFW rates. It's a binary outcome. It's either ABC or DFW. So I could use what I just did above to group into ABC, DFW. I could do just two groups. And then I could do what's called a logistic regression to predict the probability of a DFW. And then the question is what characteristics affect, if I'm predicting that, what characteristics affect my model, which is predicting the probability of a DFW. But instead of that, let's suppose you wanted to predict, maybe you wanted to predict, and maybe we'll still group, AB as one group, C as another group, and maybe DF as the third group. And let's sort of eliminate the W's for now, because I don't know exactly how to order that. But now we have an order. First of all, we could group the AB, C is already itself, and DF. So we'd have three groups, but they're ordered. So if I do a model to predict this, I can build a model that uses that ordinal information, and I will get a better model than if I ignore it. Now, that's the type of thing that's taught in Stat 555, categorical data analysis. Those types of models where you have ordinal outcomes. Of course, you can also have ordinal inputs. That is to say, I could have an ordinal predictor. And usually, in that sense, we usually don't change the model so much as we change the interpretation of the various levels and how they affect the outcome. So, if you've had Stat 512, for example, you may take a numeric variable and chunk it into 3 groups, low, medium, and high. So you have these boundaries. And if you did that, and you concluded that you've now created a factor, but it's an ordinal factor, and it's a predictor in a model now. And so if you did that, you'd have 3 groups, but they're ordered. So what we have to do, and you'll see this later, is we have to create dummy variables as part of this prediction model. But the dummy variables we create for the prediction, if they're ordinal, will very likely be different than the dummy variables we would create if, in fact, they're just a factor and they're not ordered. Because the inferences we make about the significance of that factor and how we interpret it can depend upon how we define those levels and we use that ordinal information. So, for example, if we have a numerical outcome, we may use what's called orthogonal polynomials. I don't know if you've heard that term in a course like 512, and maybe you haven't had a course like 512, but the point is that we often use ordinal information. Okay, let's go on. So we talked about list briefly. List is very important. A list is a recursive structure. I'll say why in a moment. And it has elements. And the elements of a list can be any OR object. Very powerful. So in this case, and you can name the elements of the list or not name them. That's up to you. So in this case, I have 4 elements. A is the name of the first one, and it has a value of 1. The second one is 17, and it has no name. The third one is a vector, 4, 5. In other words, I have a function there, 4:5, which expands out to the vector 4, 5. So the third element is a vector. We named it B. And C is the name of the fourth one, which is what? It's a character string. So we've mixed and matched all kinds of things there, right? So let's print this out and see what it looks like. So if we print it out, this is the way it prints list. It prints the components of the elements of the list. And so it prints A with its value 1. Now notice the second component. Notice it used a $sign A. And then we didn't have a name, so it uses double brackets 2, which has a value of 17. Now, there are various extraction operators in R. There are basically 3. There's the single bracket, the single square bracket, the double square bracket, and the $sign. We use the $sign for named components. And typically we use the square bracket, for example, when we're doing vectors. But when we have to drill down one more level, we use the double brackets. So these are, and then B it's a vector of 4 and 5, and C is a character string of 5. So that is that's a fairly, well, it has certain components, but that's still a very simple list. Because as I said, any element of the list could be an R object. It could be a very complex object. And in fact, it could be another list. And that is why we call it recursive, because lists can be defined in terms of lists. In fact, it's very general because I can define a list. I can have any R object inside that list, which in turn, if it's a list, it could have any R object inside it, which could be a list. And you could go infinitely down. An element of a list could be a list, which could contain a list, which could contain a list, and so on. If, in fact, you have a tree structure, and we think of a tree structure, and that's a very important part of statistics, when we're doing classifications. And if you take the machine learning course, where you're trying to classify by, you keep splitting. You take a group and you split once, you take each group and subgroup and you split again. And if you do binary splits, which means each time you split into two, that's what's called a tree structure. I mean, there are more other tree structures too, but that's a tree structure. You can represent it recursively, and you can represent it as a list. And as I said, that's a very important structure for the machine learning, statistical machine learning, data mining people. Let's do another type of list. Oh, yeah. What did I do? I created an list L2, which says, mn is equal to mean. What is mean? It's a function. And var is equal to var. That may seem strange, but the name of the element is var, but it equals the value is a function, the variance. It's the variance function. These are the way R, if I say mean of something, like the mean of a vector, it computes the mean. But how does it do it? Well, R, the mean function, is not written in R. It's written in C code. And what this says is, it uses a method mean. It doesn't show you the actual code. Okay? It doesn't show you the actual code. Now, the var function is partially written in R code. This is R code. But at the very end it says .call. That's calling an external function written in C. In other words, the var function, when I say I want the variance of some vector, the values of a certain random variable or variable, when I want the variance, it calls that function. But that function ultimately calls a C function. But part of it is in R code. Now that's a very powerful thing, because in R you can kind of mix in C calls with R code. You can actually mix in Java, and you can mix in Fortran. Yes, Fortran. I learned to program in Fortran in 1964. So that was almost it at the time, unless you were programming what was called assembly language, which was a very low machine level language. But assembly language for the geeks of the day. However, what I'm interested in, suppose I now say L3 as a list. And the elements of L3 are L2 and Y. But what is L2? It's a list. So in other words, I have a list inside of a list. So what happens if we print out L3? Well, you see what happens is it's going to define, it defines L2 as before, but then it defines Y as we had defined it before. So, in other words, it has this list structure here for the first element, but then it has Y, which we previously defined as a list. Now, this may seem a little bit esoteric, but as I said, it's actually very powerful. So the list is the most flexible data structure in R. And you can represent almost anything you want using lists. As I mentioned, there are two object systems in R that are commonly used, S3 and S4. S3 classes almost always return, or functions define it using S3 classes, almost always return a list object as the output of the function. It makes it extremely, extremely powerful. So earlier on, well, here I'm creating a list. The first element is 1 to 3. The next is A. The next is 3 to 9. I didn't name them. In this list, I just gave different types of representations of the vector 1 to 3, the character string A, the vector 3 to 9, and the mean, which is a function. And now suppose that I say dimension. What does dimension do? Well, I think we talked about right here. We defined a vector, 1, 2, 3, 4. And this is what it looks like if I print it out. And then we said the dimension, which defines an attribute for the vector. So the dimension is a function, but it also becomes an attribute. The dimension of x, we're going to make 2 by 2. So it's a character vector 2, 2. Now I could. Are you restricted? I'm actually converting the vector into a matrix that's 2 by 2. So the vector is of length 4, and I'm going to make it into a 2 by 2 matrix, which still has 4 elements. Suppose I had 8 elements, and I want to convert it into a 3-dimensional array, which is 2 by 2 by 2. So what does that mean? Think of a matrix as 2-dimensional, and now think about having, a second plane. So I have 2 rows, 2 columns, and a depth of 2. That's what's called a 3-dimensional array. How would I do that in R? I would use dimension, but then if I wanted 2 by 2 by 2 and I had 8 elements, how would I do it? I would say C 2, 2, 2. It would create a 3-dimensional array. You can create any dimensional array in R. And not only that, you can operate on multi-dimensional arrays. You can think of a matrix as just a 2-dimensional array. So if I did that, if I had a 2 by 2 by 2 array, I would have a plane that's 2 by 2 and another plane that's 2 by 2, which forms the third dimension. When you do a contingency table, you have rows and columns, right? Suppose you have 3 factors, A and B. And A is a factor and it has, say, 3 levels. And B is a factor that has 3 levels. So what is a contingency table? So if A has levels A1, A2, and A3, and B has levels B1, B2, and B3, I have a table, and what I typically get is a count. How many individuals are A1, B1? How many individuals are A1, B2? How many individuals are A1, B3, and so on? You get a count, and you look at this contingency table, and then what you might do as a significant test using a chi-square to see if there's a relationship between A and B. But suppose you have a third factor, C. Now you got A, B, and C. I could represent that as a three-dimensional, as a three-dimensional array, where I have the frequency counts of the three factors A, B, and C. So R is quite general. So in this case, if I say the dimension of X is 2 by 2, and then I print out X, it now is a matrix. And by default, it prints it by columns. First column, then the second column. But you can actually, if you look at dimin, the function dimin, you can actually do it by rows if you want to. That's one of their arguments. And then if I look at the type of. Now the question is, if I have a list object that has 4 elements, can I make it into a matrix? In other words, can I use the dimension function on a list? I mean, a list is sort of like a vector. There are a few differences. Like a vector, everything in the vector must be of the same type. So if they're numbers, all must be numbers. If they're character strings, they all must be character strings. If they're trues and falses, logicals, they must all be logicals, and so on. Not true of a list. It's sort of like a vector, except everything could be a different class. But does the dimension function work on a list? Where am I? So, did I do the T1? Well, I did it a while up, so let's do it again. Now I'm going to do a 2 by 2, and then let's print out T1. So what it does, it prints out, it first of all says that in the 1, 1 position, the 1 colon 3 is an integer vector of length 3. That's in the upper left. Then the next one printed out is the character string A. That's in the 2, 1 position, the second row, first column. In the 1, 2 position, the first row, second column, is the third element, which is 3 to 9. That's an integer list. That's an integer vector of length 7. And then finally, it has a question mark because it doesn't know the type. It's actually a function. But it's just saying, I don't really know what that is, at least using as it tries to evaluate it. Okay? So in other words, I can operate in some ways on a list, the elements of a list, in much way that I can the elements of a vector. Now, I want to talk about environments. Important topic. Important but not easy. Important but subtle. Important but disastrous if you don't know how environments work. I can create a new environment called E1 simply by saying new.env, which is a function which defines a new environment. Hash equals true means that it's going to define an environment as symbol value pairs. You have a symbol, and each symbol has a pair. Now, hash tables in computer science are very important. And R has a certain implementation of hash tables. Now, what I'm going to do now is I say, okay, I've defined an object, E1, which is an environment. And I said that this environment is going to consist of symbols and the value of the symbol. So I want to define a symbol A, which has a value 10. So I say E1 $A, which ties A to the environment E1 and gives it a value of 10. Now there's a function ls, and the ls function will list, you may think of it as just, people do ls, and they almost always are saying, well, what's in my global workspace? So you do ls. So suppose I just do ls. What did it give me? What did it give me? It gives me what's in my workspace. What gets defined. Now, if I say ls of E1, this is a separate environment, the only thing that's in E1 is A. So ls tells me what's in an environment, which in this case, the only thing there is A. I just defined it. That's it. I didn't define a B or anything else in the environment. I could define lots of things in this environment. Now, suppose I want to know the value of A. That's where the double square brackets come in. In other words, A is the name, the symbol, but if I want the value, I use the double square brackets to extract the value of A. So I said that there are various extractive functions: the square bracket, the double square bracket, and the dollar sign. The dollar sign is extracting the name of the symbol, but the double square brackets is extracting the value. Okay. So now there are other ways. We can do this. We can actually define attributes of environments. So I could say I want to create a new environment, E1, which actually just overwrote the other environment. And I could have an attribute of E1, which I'll call foo, which has a value of 10. Okay? So if I have E1 $foo, that's defined, but it's not going to give the value using the dollar sign. Okay. So let's print out E1. Print out the whole thing. E1 is an environment that has an attribute foo, which has a value of 10. And now, suppose we say E2 is equal to E1. And now, suppose I say the attribute of foo is 20. Okay? And then if I print out E1, I get 20. Now, this is a little subtle thing. I created an environment E1, and then the question is, did I copy that environment? Did I create another copy of it? Or, in fact, is it the same? Is E2 really the same as E1? In other words, I said that E2 equals E1. Now, normally what happens in R is you create a copy. When I do that, I create a second copy. So, in fact, I showed that in the previous lecture, that if you deleted the other, it's still, once I had copied it, it was a separate copy. In this case, I had defined an attribute foo, which was a value 10, and then I said, okay, now E2, I create an attribute foo, and I give it a value of 20. But now notice the attribute for E1 of foo is 20. What happened to the 10? You see, I never replicated the environment. And this is what's called pass by reference, as opposed to pass by value. Now, R, for the most part, when I give a function, and when we look at functions more carefully, and I'll show you this in a minute, R is mainly a pass by value environment. That is, we pass the values to a function. But a lot of times you have a big data structure. You don't want to. You want to point to it. You don't want to replicate it each time. And so it's very efficient sometimes to pass by reference. And so this is a mechanism using environments that R uses what's called pass by reference. Now, this is getting a little bit technical on the computer science side, so it's not something that's going to be critical. But later on, we may bring this up within the context of some programming examples. So, I wanted to get down. Okay. Let's do this again, because I think this is the relevant. This is perhaps what I'm now going to do, not quite so abstract and very relevant. This you do need to know. Suppose I define a new environment, E1, and I define Z within that environment, which has a value of 10. So within this environment, I've defined Z. It only exists within this environment. And now I'm going to create a function. So in a simplest way, if I want to create a function, I use the reserved word function. And I have to name the function. So what I'm saying is f equals or gets function. In other words, I'm going to assign this function to the symbol f in this case. And this function has one argument, x. And then in braces, the curly braces, I define the body of the function. In this case, the body of the function is trivial. It has one expression, x plus z. Suppose my function f of x would equal x. Suppose I didn't have x plus z, I just had, well, we could do this. I'm going to redefine it, but suppose I say f gets function. And so what we're going to define is of one argument x, and then the body is x. Suppose I define that, and then I say f of 2. It returns 2. If I say f of 10, it returns 10. Now where is f defined? What is f's environment? It's defined here in what's called my global environment. There's environment dot global env. And it's this. So if you look here, at the very bottom you see f of x. It's defined there, in that environment. But suppose I want to create my own environment and define that function in that environment, not the global environment. I mean, you don't know what's in the global environment, so you have to be careful. I mean, there's a concept that some of you have noticed called namespaces. It would be very easy for me to write a function where the symbols I use may conflict with a function you write. So we have to make sure that the symbols that I use in, say, my package don't conflict with the symbols that someone else uses in their package. And therefore, we create a namespace to make sure that my symbol names are tied to my environment by my package and not someone else's symbol, which may be the same, which is in their package. So we have and we'll get to this concept of namespaces, but do you see what I did? That's about the simplest function you could define, right? F of x equals x. I mean, you could make it a little bit harder. I could say f of x is x plus 2, right? I could do that. And now if I say f of 10, whoops, where am I? It's 12. But R knows how to evaluate 2. you pass x to it, you pass the value, and that's what we mean by pass by value. I pass the value x, which is 10. I pass 10 as the argument. So x gets assigned 10. It knows what x is now, because I passed it 10. And then it adds 2 and gets 12. Right? No problem. But now let's define this little function. I'm going to run that. So I run that. I have f of x is x plus z. Okay, I'm going to pass that function. So let me show you what will happen now. Suppose I now say f of 10. Okay. We have a problem. So we don't know. It created a vector of 10. It's strange. In fact, we don't know. It doesn't know what z is. Of course, from that message, you can't tell that's the problem. And sometimes when you're debugging, you may get strange messages that don't necessarily help you out. So what I have to do is I have to define f's environment, which I will define as E1. So I'm going to define the environment for f to be E1. Okay. Now, let's define f of 10. It's 20. Why? What's the difference? You can think of this environment E1, and f is now defined inside of it. If it can't, it has certain symbols that it has to evaluate. It has to evaluate x and z. So it says, how do I do x? Oh, that got passed to me as a parameter, as an argument. How does it get z? It's not in my function. It wasn't passed to me. I will look in my environment. Can I find z? Yes, I can find z, because I defined z as part of that environment. So it found the value of z, which was also 10. So here's the function. When it could not find z within the function itself, if it wasn't passed to it, well, wasn't defined somewhere in the function, it said, okay, now let's go out and look. See if we can find it at the next level. Now, technically, you can have environments within environments. So you keep sort of going out. Okay. Now, if I now say, let's redefine z to be 20, and now let's do f of 10, it's now 30. So now there are other couple. You'll probably be glad when we get off this topic. But there's an RM function which removes objects from an environment. Now, typically I use RM to remove objects from my global workspace here. So if I say you remove y, RM of y, it removes this y. Now, this is another reason that your workspace is an environment. It's the .global environment. And you'll see that in a second when we get to the next section. But this is why I try to be careful that I make my global environment in the directory I'm using. So my file that has code is in a certain directory. I set my workspace to be that directory. Therefore, any R objects created are in that directory. Now, the problem is, if I just look at the directory, so if I go look at the files, do you see the R objects? No, they're hidden, but they're there. In Unix, let's see, I'm trying to remember in RStudio. in Unix, I'm now in Unix, and I gave a Unix command pwd. That means print working directory. So what directory am I in? I'm in Chapter 2 Notes of Stat 323, right? I mean, this is kind of given a long thing. Network servers, Mozart's the name of our main server. But we have Bayes, J. Harner. Remember, even though I'm on RStudio, my home directory is actually on Mozart, but it gets cross-mounted with all other servers. So I have access to my stuff on any other server because we cross-mount them. Otherwise, if you had a directory in RStudio and you did some of your stuff, and you had another in SAS User, and you did some of your stuff, and you have another on Mozart and did some of your stuff, and all of a sudden now your directories, you don't know which is, we don't do it that way. We have one directory structure for each of you, and when you get an account, you get a directory, but it cross-mounts to any system you're using. So if you're doing the SAS course, same stuff is there. If you're doing the R, same stuff is there. You have one directory, one set of data, and that's actually one reason you might consider, using our servers as opposed to your local machines, because all of a sudden your local machines now you have another directory, and stuff gets out of sync, and you don't know which is. You've got the same files, and you don't know, you edited one and not the other, and then you forget which one you edited, and you don't know which is the latest one. Now you might figure it out by looking at the dates it was modified, but the point is it becomes a nightmare. It's one of the reasons people use Dropbox, because Dropbox cross-mounts across everything also, except that it's a little tricky to cross-mount it to a server. But if that is true, let me do an ls. So I do an ls. That's a Unix command. So if I do an ls, there are the files. Now those files are exactly the same as I have here. But now let's do something else. Let's do ls minus l. Well, that prints the files, same set of files, except I give more information. Now, these numbers are the permissions for each file. So this tells me the size of the files, when they were created, and the names of the files. This first thing over here says, you notice that there are 10, there are 10 slots there. The first one is a dash. If it were a directory, it would have a D. But if it's a file, it just has the hyphen. Now the next three, read, write, and the next three are my ownership permissions. It says, for this file, I can read it and I can write it, and the third one means, can you execute it? Well, these files are text files. They're not executable, so it's a hyphen. Now the next three is read hyphen hyphen. That's my work group. If I'm in a work group and I'm sharing files among people, this would say anyone in my work group can read it, but no one else in my work group can write to it. Now I could set it up so that people in my work group could also edit my files, and therefore it would, in that case, it would be in that second group of read writes, it would be an RW hyphen. And then the third group is the world. So if that were read write, that would mean, in fact, you could come and edit my files on my account if you could get into my account. But you'd still have a problem because you wouldn't be able to get through the directory structure because they also have permissions. But you can set the permissions using, and there are commands in Unix that do this. This particular thing is very common when you have files where I can read write and others can read but not write. But that doesn't mean that you can actually get there to read it, because you would have to have execute permissions on my directory structure to even get here to do it. So you wouldn't really be able to do it. But I can make certain directories public, meaning I will give you the permission. So at any rate, if I now do an ls, suppose I do an ls minus a, ls, you notice that some additional files now. And notice that there's one, for example, rline.r, .dsstore, and and so forth. There are some additional files that are what are called hidden files. And so that will give you the full access to what's in that directory. So, at any rate, I'm not going to do more on Unix right now. We may do a little bit more off and on, but let's see, what time is it? Okay. So if I now look at remove, going back, I'm going to remove E1. If I remove E1, the question is can I still evaluate it? And the answer is I still can. Even though I removed the environment, it didn't actually get rid of it. It just removed the binding for E1. But you can still actually get to it. So REM is sort of special. And I still have the function, and it's still the environment is specified down here. Okay, well, this has been a little bit technical, as I said. What I'm now going to do is, this finishes this section. You should sort of work through the code on your own and read the book carefully. Now, what I want to do now is to go back to chapter 2 and look at the third section and start doing that. So here's the third section, and I'll get rid of section 2. And I'm going to go down and set the working directory. Okay. So now if I look at the workspace, I want to clear this workspace. Okay. There's certain general things that the word capabilities simply tells you. What is this machine capable of doing? It can do JPEGs, it can create PNG files, the JPEG, the PNG, and the TIFF are graphics files. It can create all three of those. Tcl/Tk is actually a programming environment that people use to develop graphical interfaces for R. If you're a Linux type person, then you know what Tcl/Tk is. X11 is a graphical. X11 is a windowing system for Unix, and Aqua is sort of an underlying windowing system for the Mac. This is actually running on a Linux machine, and so this tells you the various things that you can do for this particular machine. Now, this next thing is not going to work, and the reason it is because GenePlotter is a library that we have not put on the machine yet. We will do this, but it's not currently there. So when I say library, remember, R has all these libraries. One of them is called GenePlotter, and when I say, okay, mount that library so I can use it, well, it says you haven't installed it. There is no package called GenePlotter. Now there is one. It's out on, it's out on what's called Bioconductor. You can actually install it quite easily, but it's not installed. So that's something I need to have Steve Giesler do. So there is a package, but it's just not installed. But what I really want to show you is the following. When I say search, it shows me the environment. It shows me what packages are involved or installed here. But notice the very first one is global environment. .global environment. That is the global environment for that we're working in. And anything you create will go into that global environment unless you tell it to go in another environment that you've defined. By default, it goes in the global environment. And then there are various packages. There's a package called tools:/RStudio. And then there's a and that's an RStudio specific functions that they have developed for this environment because they have some very specific things. You also have a package called stats, which does a lot of basic stat analyses, a package called graphics, a package called devices, utility packages, data sets, methods, and so forth. Now, each time you load a package, it would appear in that list. So if I load a package, it would appear in that list. Now, But you can only load packages that have been installed on that machine. And only certain packages have been installed. So what I will be doing as we go through the course, I'll be installing, or have Steve install globally, certain packages that we'll need for the course. We actually need GenePlotter, so we need to install it. Now, can I see what's in this? Can I see what's in these packages? Well, you can use the ls. So if I now say ls, if I say ls of, well, let's suppose I say ls of 2, then this actually shows me what's in RStudio's package, the tools. Okay, so that's showing me what's inside the second element. If I say ls of 3, you see there's a lot of built-in statistics. So these are all the statistics that are built in to the statistics package. So the statistics package is quite large. These are all the built-in functions and data sets that are in the base statistics. In other words, it's built into R. You don't have to worry about that package, stats. It's there. It will always be there. You don't have to load. You don't have to load it. It's there. So you can see there are a ton of things. There's one called binomial Bartlett's test. You may recognize some of those. AOV.GOM, that's the analysis of variance for GOMs and so forth. So there are tons of these functions representing things you can do in Aura out of the box without installing any package. So for example, suppose you want to do a t-test. Well, there just happens to be a function called t.test, which will allow you to do a one-sample t-test. Actually, you can do a two-sample t-test also. You can do a one-sample t-test, a paired t-test, or a two-sample t-test of t.test. And so if you wanted to know, okay, well, how do I use the t-test? Well, you go to help, and you type in t.test, and you look for help, and you go here, and this tells you how you use the t-test. You can have two arguments, x and y. If you have two groups, an x group, you have two groups, an x and a y group, and I do want to do a two-sample t-test. But by default, it says y is null. By default, it says there is no second group. It's a one-sample t-test. So by default, you're doing a one-sample t-test. But if you have a second group, it would be the second argument, which is y. So you have two vectors. The first vector is the one sample, the second is the second sample, and you would be doing a two-sample t-test. By default, if I'm doing, it does a confidence interval by default. By default, it does a 95% confidence interval. By default, it assumes the variances are not equal. So when you take your elementary stat course, what did you assume? Doing a two-sample t-test, what did you assume? You almost always assume that sigma 1 squared equals sigma 2 squared. You assume the variances are the same, right? And if you did that, you could get S1 squared and S2 squared and pool them into your pooled estimate of the variance. And you did what's traditionally thought of as the two-sample t-test using a pooled estimate of variance. And that was assuming that sigma 1 squared equals sigma 2 squared. That was an assumption. And you're also assuming normality, probably, for both groups. Now, of course, those are all assumptions you should check. The fact that you assume them doesn't make them true. So if you're doing a two-sample t-test, you should check, are they normal? How do you test it? You probably test it with what are called normal probability plots. How do we test that the variances are the same? Well, we can do an f-test to test sigma 1 squared equals sigma 2 squared. There are other ways you can assess that, but that's one way. By default, it assumes no. It's going to do a modified t-test where the assumption of sigma 1 squared, sigma 2 squared is assumed not to hold. And notice that the alternative hypothesis could be two-sided. It could be less or greater. So you could have a one-sided or a two-sided. And by default, if you're testing, it tests mu equals 0. So if you want to test mu equals something other than 0, you simply say mu equals whatever you're testing. In the previous class, we were testing when runners hit the wall in a marathon. A marathon is 26 miles. And the hypothesis is they hit the wall at 17 miles. So you can test the hypothesis at mu equals 17. You collect data from a bunch of runners, and you say, okay, when do they report they hit the wall? And apparently this is very physiologically something that you know. When you hit the wall, you know it. So if they tell you, well, I hit it on this certain block of this street, you know how far they ran, so you know when they hit the wall. So you collect the data, and you test the hypothesis mu equals 17, but by default, it will not assume, in this case, it's a one-sample test, and so the variance equal isn't relevant here. Okay, so this is how you use the test. Now, just to, let's continue on. There's a built-in data set called cars. Suppose you want to know a little bit about cars. I could say head of cars. Does anyone know what that will do? Prints out the first 6 values. So this is a data frame that has 2 variables, the speed and the distance. If I say type of cars, more fundamentally, this says that a data frame is a type of list. It is. A data frame is a type of list. All the elements of the list must have the same length. And within a list, they must be of the same type. But the first element could be character and the next one could be numeric. That's okay. But for the second element that's numeric, everything must be numeric. So in other words, both of these are numeric. And that's fine. So this is a data frame that has 2 variables, both of which are numeric variables. There's another way I can get information about a list. I can say structure, STR, the structure of cars. And that says it's a data frame with 50 observations and 2 variables. And then the 2 variables are listed. Notice a $sign. It's extracting from the data frame the two components, speed and distance, which are numeric, which have, and it gives the first so many values, but then it has ... So it's not necessarily giving you the full set of data. So it's giving you an idea of what the structure of this data frame looks like. So this is a very quick way of learning about a data frame. And suppose you want to know, and this can become important, suppose you want to know the size. This data frame, cars, is taking up 1576 bytes. Now, for big data, this becomes important. Now, by default, OR keeps its objects in memory. And so if you've got a machine that has 4 gigabytes, well, you pretty well know what the upper limit is of what you can store. If you've got a petabyte of data, you're not going to put it in memory. You've got to deal with it another way, which you can, but you're not going to just do things within memory with a petabyte of data. Petabyte is a lot. Not so much for astronomers, though. A petabyte becomes fairly common among astronomers. So, well, I've already done the head of cars. So if I do head of cars, and then the tail does the last 6. Okay. Well, this is probably, we're going to get into a lot of things relating to the language now. And so I think this is probably, it's time to stop, right? Yeah. So what you should do is be working through this. And what I'm probably going to put up, I'm going to put up some assigned problems. And what my intent would be that at some point, some subset of those assigned problems will be your first project. Okay? So I'm going to give you more than I'm going to grade. But I'm going to give you some of the assigned problems in the book so you can start playing around with them. So I will be putting that up on the schedule, what the assigned problems are. But when I give the assignment, you will actually get a template that you then can sort of move the barcode in to actually do the assignment. So, any questions? Okay, I realize that the environment ideas were a little bit esoteric, but it's important to understand, but you don't have to fully understand some of the concepts I talked about today straight out shoot. We'll come back to some of these concepts, and some of the concepts are more important than others. The idea of a function being an environment and how it evaluates things is important. So when I define that function of x plus z, and where did it get the value of z, that is important. Okay.